Physics students, this is the final video out of 4 for topic 4.4 wave behavior, and this is a pretty big video. It's going to last a little while, so you might want to break it up into a couple of sections. But what I want to do is I want to talk about a couple of sort of mysterious things which you may have I don't know, you may have seen this before or studied this topic before. I'm going to talk about interference patterns of light in 2 particular cases. I'm going to focus most of my discussion on what's called double slit diffraction, which is light, or we're going to talk about lasers, coherent monochromatic light, passing through 2 narrow slits or openings, and what results on the other side, on a screen on the other side, in terms of an interference pattern, okay? So you want to really watch this video carefully and take very, very close notes on this, okay? Now, remember, at the end of the last video, I presented you with this particular diagram, which shows wavefronts from 2 different sources and spreading out. And we talked about how at point P there was constructive interference, and at point Q there was destructive interference. And what I actually did was I measured the path lengths from S1 to P and S2 to P, and same thing for Q. And I showed that the difference in path lengths, as measured in centimeters, ended up satisfying those conditions for constructive interference and destructive interference that we talked about before, okay? Now, if you imagine now that these 2 sources are now 2 coherent light sources, meaning they're in phase, as I discussed last time, could be 2 identical lasers, or it could be 1 laser where that beam has been passed through 2 narrow slits of equal width, okay? And if you set up a screen on the other side, what would you see? Okay, well, remember, in this particular case, before, we said that where crests line up, you would have, because intensity is proportional to the amplitude squared, where you have a higher amplitude, you have a higher intensity. So you would see a bright sort of fringe or a bright sort of strip of light on the screen directly opposite along this axis, which is a line drawn perpendicularly to a line drawn directly between sources S1 and S2, okay? So again, you see the analogy between water waves and what we did the last time in terms of where crests or troughs line up, okay? Now, you would also see a pattern. You would see another bright strip over here and another bright strip over here, and in this second bright strip, that's where point P would be, where we talked about point P being an area of constructive interference from last time. There's also a corresponding bright fringe or bright strip over here, okay? You can see that there's another place over here where they line up. You see that? It's bright over here and bright over here. So pretty cool stuff, all right? Now, bright, 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 bright. Now, what's going to happen directly in between them? Well, you're going to have dark strips or dark fringes where there's perfect destructive interference, because you have a crest overlapping with a trough at those places, okay? So you're going to have an alternating sort of system of bright strips, dark strips, bright strips, dark strips. And in fact, that is exactly what you see. This is so cool. That's exactly what you see when you shine a laser beam through 2 narrow slits. You see a pattern of bright and dark, what we call fringes, okay? Now, the brights are maxima, the darks are minima, and I want you to note a couple of things. There's always a maximum along the center line between the 2 sources. That's the first one I talked about. And the central maximum is always the brightest, since it's the most intense, okay? All right, and in fact, this is what a double slit diffraction pattern looks like in real life, okay? Don't worry about the dark areas here and why there's like a bright and then a dark set, okay? We're going to study those later as a higher level topic later on in topic 9, okay? All right, so the first person to study this phenomenon was named Thomas Young, and he was a British physicist in 1801, and he did a very famous experiment called, which is now called Young's double slit experiment, okay? And what he did was he effectively demonstrated the wave nature of light by showing that there's an interference pattern between 2 light sources that interfere exactly the same way that water waves, for example, interact, okay? This was a demonstration of the early wave nature of light, okay? If light were a particle only, he would have seen only 2 bright fringes on the screen, which would be the same width as the slits. You'd see bright here and bright here because the particles would just shoot through here and stick to the screen. That is not what he observed. At any rate, it enabled him to determine experimentally, for the first time ever, the wavelengths of light. And he utilized a single slit to ensure that light from only one direction fell on a double slit, or otherwise the pattern would be washed out. There would still have been a pattern, but it wouldn't have been as easy for him to quantify. And it's important for you guys to note that S1 and S2 act as coherent sources since they originate from the same primary source. Okay? So monochromatic and coherent. That's crucial in seeing an effective interference pattern that you can actually quantify. Okay? Now let's take a much closer look at Young's double slit experiment. Okay? Recall the conditions for constructive and destructive interference in terms of multiples or half-integer multiples of the wavelength, okay? Now, it's easy to see why the central bright fringe is bright, okay? It's because we have symmetry here where L1 equals L2, okay? So in this case, n is 0, so L1 minus L2, which is the path difference, is 0 lambda, okay? Now, the first bright fringe would be n equals 1, okay? And it's going to be located up here where this path difference right here is going to be exactly one wavelength, okay? And that's 1. Now, the first dark fringe, which would actually be n equals 0, okay? It's a little bit confusing in terms of what we refer to as the first bright fringe, first dark fringe, and the central. The central bright fringe is n equals 0. The first bright fringe is n equals 1, but the first dark fringe is n equals 0. Okay, you might want to pause the video and replay my explanation of that. That will become very important for you, especially if you're a higher level student in our later studies of this, okay? At any rate, the first dark fringe, the conditions will be such that this path length difference between L1 and L2 has to be a half of a wavelength, and you can see that that has to fall on the screen between the central bright fringe and the first bright fringe where n equals 1. How cool is that? That explains something that was so mysterious in physics, and Young really did a lot towards us understanding the wave nature of light back in the early 1800s. Let's take an even closer look, okay? We're going to have to make some simplifying assumptions here in order to really understand and derive the equation and allowing us to quantify Young's double slit experiment, which is required of both higher and standard level students, okay? Now, here's L1, L2. I'm basically just zooming in on what's happening opposite these two slits, okay? And then this is kind of a bigger picture. So I'm defining some variables here. Capital D is the distance between the slits and the screen. S is the distance between the central maximum or center line to a particular fringe, the center of a fringe, and little d refers to the distance between the slits or the slit separation, okay? And of course, lambda is the wavelength of the light, okay? Now, a typical value of the slit separation would be on the order of about 1/10 of a millimeter, okay? And I want you to note here that in this case, L1 is less than L2, okay? You see that, how that's written there? All right, now, make a couple of assumptions, which is going to help with our trigonometric treatment of this, okay? Assume that the distance to the center of the screen is much, much, much greater than the slit separation, okay? So what we're going to do is we're going to treat L1 and L2 as if they are parallel, making equal angles with the horizontal, okay? So that's why we can say, we can draw it like this, parallel, with this angle being the same for L1 and L2. And what this means is that the angle S2, S1Z, which is right, S2, S1Z, right there, is theta, okay? And it means that, making a little right triangle right here like this, okay, the path length difference is S2Z, which is d sine theta, okay? Now, if you remember the conditions for constructive interference, this means that d sine theta has to be n lambda, where n is an integer multiple. That gives a bright fringe or constructive interference, okay? Again, d sine theta equals n lambda, okay? Now, it turns out that if theta, the angle, is very, very small in radians, and you can test this yourself on your calculator, this is called the small angle approximation. And the sine of theta is approximately, to a very, 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 very precise value, is the same as the angle, which is the same as the tangent. And if you think about how the sine and tangent are defined in terms of your unit circle and the angles and all that, this makes sense, but it only works for very small angles. Why is theta so small here? It's small because big D is so much bigger than little d, okay? Now, note that theta increases for every integer in outwards from the central maximum. It fans out or spreads out on either side of the central maximum. And for the nth pattern, note that tangent of theta, which is equal to sine theta because we're using a very small angle, is equal to S sub n, where the n refers to the number of the fringe, or the distance for that particular number of fringe, where n equals 0, 1, 2, 3, 4, all over d. Just think about your geometry. It's actually pretty simple geometry, okay? Now, in other words, S equals d sine theta. But since d sine theta equals n lambda, I put it all together and I can say that, well, S sub n, or S, equals d n lambda over little d, okay? Now, in your data booklet, you're given this equation, and this is the manner in which you're supposed to quantify it, okay? Which means that in this topic, as a core topic, which is common to standard and higher level, you don't need to deal with different order numbers of fringes. We always just consider n to be, we just deal with the first dark fringe or the first bright fringe, and we take n equal to 1, okay? But you guys need to, especially if you're higher level, you need to be aware of how that n can actually vary, and that gives you what physicists call the nth order fringe, which is like one of those weird sort of physics phrases, but it obviously makes sense in this particular case. All right, let's do an example. Pause the video and see if you can do this one on your own. Okay, so double slit experiment, a source of light of unknown wavelength is used to illuminate two very small slits 0.15 millimeters apart. So they're giving you the distance to the screen, and they're saying the bright spots are observed separated by a distance of 4.95. What color of light is being used? This is exactly what Thomas Young did. He used this equation, and it turns out that lambda is about 570 nanometers, that meant that it's a greenish yellow light, or a greenish yellow coherent monochromatic source. Pretty cool stuff. Okay. Now let's talk a little bit about the intensity of light in double slit patterns. Okay. It turns out that the bright fringes are all equally bright if the slit widths are of negligible size. And if that sounds kind of hocus pocus and nebulous to you, it is. Later, as higher level, we're going to talk about what that means, negligible size. For standard level, all you need to know is that the bright fringes are all equally bright, and you can assume that the slit widths are of negligible size. The ID might ask you qualitatively what would happen if they're not, and I'll explain that to you right now, okay? So distance from the center of the screen, here's your bright central maximum, and here's your minimum maximum spreading out from either side, okay? The vertical axis units are arbitrary here, intensity, okay? All right, so note again, same brightness, same fringe separation. Now, if they're not negligible, what happens is that you have bright fringes of varying brightness that falls off as you go away from the central minimum. However, you have the same fringe separation. So you better know that, okay? Because that's something that could easily be asked of you in a paper 2 question, okay? Very interesting, okay? Now, let me ask you this. What effect does a higher frequency or a different color light have on the interference pattern? Think about that, okay? Let's see. So here's your red, which has a lower frequency. Here's your green, which has a relatively higher frequency. What do you notice that's different about these two? Well, look, the green is kind of squashed closer together, which means that S is smaller. Well, why is this? Is this what you would expect? Of course it is, because S equals d lambda over little d. So S is proportional to the wavelength. In red, you have a lower frequency, so you have a higher wavelength. Therefore, because of this relationship, you have a larger fringe separation than you do with green, which has a higher frequency, therefore a lower wavelength, and they're squashed closer together. How awesome is this? Okay, it's so cool, and it makes sense. It's beautiful. Okay, all right, try this example on your own, and then I'll go through it. Okay, so this is a Young's double slit experiment. This is the kinds of questions you would be asked on a standard level test, which of course is fair game for you higher level kids, all right? So in part A, well, first of all, they give you an intensity distribution like this, okay? And they give you the wavelength, the distance from the slits to the screen, and the separation of bright fringes. Calculate the separation of the slits. Well, remember this situation and the difference between big D and little d and S and what those mean. Putting all this together, you have a separation of the slits of about 1.5 millimeters. Okay? Now, if the laser is replaced with one producing a lower frequency of light, would the fringes be different? Of course they would be. The fringes would be further apart. They'd be spread out. And then a source of white light, kind of a trick question. there would definitely be changes to the fringes on the screen. Mainly, there would be no fringes at all because white light is not monochromatic and it's not coherent, okay? So this is the nature of the kinds of questions that you might be asked, okay? Now, I'm going to talk about single slit diffraction, okay? Now, listen carefully to my words, all right? If you're a standard level student, you do not need to quantitatively describe single slit diffraction, okay? You do need to quantitatively, meaning calculations for double slit, but not single slit. If you're higher level, this is all fair game, but you'll quantify single slit diffraction later in topic 9, okay? Now, remember diffraction. Geez, we've been talking about diffraction and all these wave kinds of things for so long. We're kind of getting sick of it, but I just have to remind you that diffraction is the spreading out of waves, and it occurs when the wavelength, and here is important, I'm calling the opening B instead of W as I was before, and this is going to be good for you higher level kids later, okay? More diffraction occurs when the wavelength is on the order of B, and less diffraction occurs when the wavelength is much, much less than B. Or in other words, when the opening is much, much, much greater than the wavelength, there's less diffraction, as you know. And we talked about how light does not diffract through a doorway, but sound does because the wavelengths are different, okay? All right? We talked about all of that. Now, we've never really talked about why exactly does diffraction happen? It's kind of an interesting thing. We're going to talk about it now. There was a Dutch physicist in the 1600s named Christian Huygens, and Huygens' principle basically explains this. And what his principle does is it treats the slit as an infinite number of sources, okay? So in this case, it's obviously not infinite. It's only 5 point sources, okay? But if you think about 5 point sources with these circular sort of wave fronts going out in all directions, the overall effect will be a big wave that comes through that ends up curving and spreading out, okay? So the overall result is the addition of all of the sources. Now, if you're savvy on my previous conversation about what happens on a screen on the other side, okay, you can immediately surmise that directly across from the opening, all of these waves are in phase, so they add up to give a maximum intensity. What this means is that a single slit diffraction pattern ends up being a very, very bright main fringe right directly opposite from the actual opening, okay? And that's shown right here, okay? So again, it's because in the forward direction, there's no phase difference. All of those little wavelets, as they call them in physics, little baby waves, little tiny waves, they're all in phase and they give a maximum intensity. So just to relate this back to something we've talked about already, water waves through a hole in a barrier, okay? There's a high amplitude wave here, and it's lower on the sides, and if we increase the aperture length, the aperture distance, we get much, much less diffraction, okay? So there was a pattern. There's a similar pattern with monochromatic light. So directly opposite the slit, there's constructive interference. The greater the amplitude, the brighter the light, because I equals A squared, okay? It's the same pattern as for water. Incredible. Light behaves like water. And that suggests that light is a wave, not just a particle. Super, super cool stuff, okay? Okay, so I'm just going to compare briefly the double slit and single slit patterns. Here's your double slit pattern from before. The single slit is very, very, very different, okay? Only the center fringe is a very strong one. The bright fringes on either side get much dimmer as they get farther from the center. And there's some important variables to consider. If you're in standard level, you don't really need to understand how these are related. In fact, I'm not even going to explain it right now, but for you higher level kids, you're going to want to take note of these 3 very important variables to consider because they're going to come up again for you, okay? So here's the intensity pattern from laser going through a single slit right here. It turns out the 3 most important variables are, number 1, the angle between the center line and the maximum and minimum lines, which is shown with the blue distance right here, and on the screen it'd be right here. Number 2, of course, the slit opening, the width of the opening, because we know that diffraction is affected by the width of the aperture through which a wave passes. We call this B. And obviously the wavelength of the light used for reasons that I just described, okay? So 3 very, very important variables, okay? All right, now, at any other angle other than the first other end than theta equals 0, there's a path difference between the rays that depends on the angle theta. And again, you don't need to understand the quantification of this quite yet, but here's that magical lambda over 2. If the path difference is lambda over 2 between any pair, destructive interference occurs, and that is why we see the dark fringes, okay? So the condition for the first minimum with a single slit is that the angle must make all of the sources across the slit cancel out. So again, standard level, you only need to know about single slit diffraction patterns qualitatively, all right? Okay, and a typical intensity versus angle graph would look like this, right? Here you go, here's your bright middle fringe, and then you have your first minimum, second minimum, etc. Here's the magical equation, which I have not derived for you guys. It's theta equals lambda over b. We'll do that later in a higher level. And I should mention to you standard level kids right now that through circular openings, we get a similar pattern, but the diffraction patterns are concentric circles, and this is called in physics Airy pattern or Airy disk. And it turns out that this has great implications for a lot of applications, such as the one that comes to mind is how starlight comes through a telescope aperture, like through a lens. You often see things like Airy patterns and diffraction patterns with light. So really, really cool stuff.